Okay, so strong and weak acids then. First thing we're going to talk about briefly the pH scale. At GCSE, it doesn't really go into this much. It simply says that 7 is neutral, and then less than 7 we call an acid. More than 7 we call an alkali. Um, and obviously on 7 it's neither an acid or an alkali. We call it neutral. So what's the difference between acid and alkali? Well, apart from the original definition was that, but we're going to learn it a slightly different. We're going to learn a different kind of definition. Let's take the simplest one and the most common one that's talked about is hydrochloric acid. What happens when you put that in water? Well, for a start, if you didn't have it in water, it's not actually called hydrochloric acid. Once you put it in water, it becomes an acid. So what is an acid? An acid is something that produces hydrogen ions, or basically protons. Obviously, a hydrogen atom is nothing more than a proton and an electron orbiting it, or not orbiting it, but anyway, we won't talk about quantum physics at this stage, but we have an electron and a proton. And once the electron is removed and it's been ionized, we are left with a proton, and then the chloride ion. So this is actually what goes on when you dissolve hydrochloric acid in water. They separate into these ions and they float around separately. And it does this completely. So it doesn't. It's not like some of them. It's not like some of them become protons. Some of these molecules split up, and some of them don't. They all split up. Maybe that might be on the assumption that there was enough water to do that with, but yeah, we'll just say that they all split up for now at this stage. Now, this is not the case for all. This is not the case for all acids, but it is the case for so-called strong acids. So you can probably guess what a weak acid does. It doesn't completely do this when dissolved in water. So the thing to what is this called when it separates into these ions? It's called dissociation. So this process is called dissociation. We can say that the ions dissociate from one another, from the molecule. Dissociation. And strong acids completely dissociate. Weak acids do not completely dissociate. So let's give an example of a weak acid. Some examples are ethanoic acid, citric acid, and I forget one of the more common ones. Just consulting my textbook at the moment, actually. So it's ethanoic acid, citric acid, and another common one that's that's often talked about is carbonic acid. So they don't completely dissociate. They don't completely ionize from one another. Let's look at ethanoic acid. So this is obviously a bit of organic chemistry revision as well. So we've got the CH3 on one end of the chain, then we've got the C, and then OOH. So this tells me and this comes up in a video I made a moment ago, in fact. So that is on the end. In fact, I'll draw the whole molecule now. That's our ethanoic acid, a carboxylic acid. It's got a carboxyl group, or carboxylic acid group. And that does not. Let's see what would it dissociate into. It would dissociate into the proton and the rest of the molecule. So, but it doesn't completely dissociate. The reason for that is because it's a reversible reaction. In other words, it might start off as 100% this. Put it in some water. I should put a aqueous solution symbol there, and these should have aqueous solution symbols as well. So when you put it in water like that, it will obviously move to that side, but because it's a reversible reaction, some of the products will will recombine and form the reactant again, and so it's not a complete. It doesn't completely form. It doesn't completely dissociate, and that is basically the definition of a weak acid. So as well as stating that they don't completely dissociate, in actual fact, they don't dissociate much at all. So if we think about where would the equilibrium lie, in other words, what percentage of this are we going to have and what percentage of this are we going to have, we actually have a lot more of this. So only a few of these molecules dissociate into this. So that's whereas in the other case, like basically all of them dissociate. In this case, only a few dissociate. Or we should say, maybe it would be more accurate to say that the equilibrium lies much more to the left. Like many more, maybe all of them will dissociate, but whilst all of them are dissociating, many of them are reassociating or going back to the reactants. So it lies very heavily to the left in a weak acid. Another thing to be clear of about here is to not confuse strength. We're talking about strong and weak acid. Not to confuse strength with concentration. So concentration would be the amount of acid there is in a certain volume, usually the amount of moles per volume, and the strength is down to how much it dissociates, how much does an acid dissociate. That's the strength of it, and the concentration would be how many moles per volume of liquid there is. So let's briefly introduce the pH scale and how this relates to what we've looked at there. Clearly, you could have if pH is going to be it represents the concentration of hydrogen plus ions or concentration of protons. So you could change the concentration of a weak or strong acid, and that would change the pH. And you could change the strength of the acid without changing the concentration, and that would also change the pH because we're just messing around with the concentration of H plus ions in both cases. With the strength, it's how much they dissociate, whereas the concentration is just how much of the acid moles of acid we put in the water. And so, in both cases, when we change the strength or we change the concentration, we are changing the concentration of the H plus ions or the protons. And what this is showing here is that as you increase the concentration, as you increase the concentration, the pH scale goes down. We know that acids have a low pH, and we know that alkalis have a high pH, and we know that acids have a high amount of protons, high concentration of protons. So this means then that as the concentration of protons go up, the pH scale goes down. So when you go to A-level chemistry, this is connected with you'll start to do logarithmic calculations, but essentially we're using powers of 10 here. So as you go from 7 to 6, the concentration of protons is actually going to be 10 times as strong. So you can imagine 10 to the power of 10 to the power of -7 and then 10 to the power of -6. But it's not as simple as that. But it's going to be something times 10 to the power, or something like this anyway. I forget the actual formula, but it comes up in A level. So as you went from 7 to 6, you're going to multiply. It's going to have 10 times as much concentration of protons. Whereas if you went from 5 to 3, you would have 100 times as much concentration. Likewise, if you went up the scale, you would reduce the concentration. So as you go from 8 to 11, you're going to reduce the concentration. It's going to be 1,000 times lower this time. Okay. So just to recap this last little bit, then, if I were to have a strong acid, then if I increase the strength of the acid, then that will reduce the pH. Or if I increase the concentration of an acid, that would reduce the pH. If I had two acids, one weak and one strong, of the same the same concentration, then the strong one would always have a lower pH. Okay, and if I had two acids of the same strength, then it's always going to be the more concentrated acid that will have the lower pH. So I hope that makes sense. I think I've covered everything you really need to know for GCSE relating to strong and weak acids. I haven't gone over alkalis here, but if you would like me to make a video on alkalis, just let me know. Okay, thanks. Bye.